Our next speaker and last speaker before the coffee break is Ileana Buhan. Ileana has a PhD from TU Twente in the Netherlands. After her PhD, she joined Philips Research for 2 years as a senior researcher. And since 2012, she is working at Riscure in the Netherlands, where she is product manager for industry training.
Thank you. So thank you for the introduction. It's an honor to be here today. It's my first conference where I have so many women in the audience, so it's a first. But today is the 4th of March, and today we are celebrating the birthday of Jane Fawcett, and who was a famous cryptographer and code breaker who, by her contribution and work at Bletchley Park, has made a definite contribution to the war outcome. So what I propose to you today is actually to take a trip in time from 1941 to 2020 and follow Jane as if she would be doing code-breaking activities. We will look at the challenges, we will look at the tools that she's using, and we will also look at some of the purposes of why she's doing these kind of evaluations. The title of the talk is a shameless plug to one of the problems that me and my colleagues have proposed for a problem that Jane will face towards the 2020 when she's using machine learning. And at the end of the talk, I will give some advice to a young me, a 15-year-old me who is coming to this field of security evaluations. So it's now 1941, and we know that Jane is one of the few people that was informed about the search for Bismarck, which is the German battleship. It's a flagship who became a prime target for the Allies after it chinked one of their war battleship. And Jane is working in Bletchley Park. They are decoding messages from the Germans using something that she's called the typex machine. And in one of these messages, it's actually the 25th of May, as history goes, 1941, she recognizes a vital piece of information that helps locate the Bismarck and then annihilate it. The main tools that people use in that time for doing code breaking were very simple. It was pen and paper. But this event, basically, it's the moment when code breaking is put on the world, and never again, after this moment, code breaking activities will be underestimated. So now let's go a little bit further. It's now 1997, and we have, at this point in time, sophisticated crypto algorithms. We have the DES, we have the RSA, and we are using hardware already to perform encryption and decryption in a blink of an eye. It's no longer possible, or it has been proven that it's not possible to break this cryptographic algorithm using pen and paper. So the best thing that Jane has, if she has to break these algorithms, is basically to do brute force analysis of the key space. And what we have here is a cluster of computer that she could use. And in 1997, to break or to brute force the DES algorithm, it would have taken, according to history, 96 days to do so, to find a key that was 56 bit long. A year later, however, the Electronic Frontier Foundation is building a machine that costs $250,000, and it's able to break the DES in approximately 1 day. But it's cost a lot of money. So this is the status of 1997. Now let's go a little bit further in time. So we are now in 2005, and Jane is sitting at her table with what I hope you recognize to be an oscilloscope, and she's measuring something on a board. So what happened in the meantime? By the way, Jane here is evaluating a cryptographic implementation, and she's probably working in a hardware security lab like Riscure here. evaluating cryptographic algorithm for markets such as payment or content protection, which have a big interest in making sure that their transactions are secure. So what happened in the meantime from 1997 to 2005 is that in 1998, there is a paper from Paul Kosher and his colleagues, who are always forgotten when this is mentioned, who is called Differential Power Analysis, and they show that it is possible to break cryptographic algorithm by simply looking at the power trace that this algorithm consumes while it's executed on a chip. And if, for example, it used to cost so much, $250,000 to break a 56-bit desk key, they showed in '97 that you can break an RSA key, which is 1024-bit long, simply by staring at a trace. I don't have the original trace in this slide, but it's easy to find. And just by staring at the trace, you could actually recover the whole 1024 bit keys of this RSA algorithm. So what Jane is doing at this point in time, I can represent it very simply like this. So she has a chip, and in the chip there is an algorithm with a key that, I don't know, do you hear me? Yeah, so I should, yeah, closer. So there is a chip who has a key that is unknown. That's why this key is in red. And Jane can feed messages to this chip, and she can also record traces. And how she's doing the evaluation is very simple and sophisticated at the same time. So it looks something like this. As I said, she's recording traces, and then she knows how this AES algorithm is implemented. She can feed whatever messages and whatever key she wants, and she has access to the intermediate variables for this cryptographic algorithm. Now, because you cannot compare directly intermediate variable or data with power traces, she uses something that is called the leakage model, which makes a translation between this intermediate and the power traces. And this distinguisher is a function which tells us which of the key is good. Now, this picture is pretty simple, and it looks like easy to do. In reality, what we are doing, it's a bit low tech. We are basically enumerating all possible keys for which we are computing scores, and then hopefully this distinguisher will tell us that the best key or the correct key has the highest scores. We never attack a full 128 keys or 56-bit keys at once, but what we are doing, we are actually attacking 1 byte at a time, which is a more manageable problem. Now, at this time, we are 2005 or 2015, and throughout the year, it's no longer a question if we can break cryptographic algorithm using side channel analysis. We know that that is possible. The question that we have is how many traces do we need to break crypto algorithms, and what kind of information an attacker needs to have about the device in order to do so effectively. So how can the attacker construct a leakage model? Also, in this time, technologies is getting smaller and smaller. Transistors are getting smaller and smaller, so the signal about the leakage is buried more and more in the traces. So Jane would spend a lot of time in doing signal processing and extracting exactly or finding where this leakage is in the traces. And at this point in time, we are using AI, but the AI or the machine learning that we are using is mostly for feature selection or feature extraction purposes. So we are basically trying to get rid of the noise in what we have in these traces. So let's move a little bit ahead in time. 2017, so it's the era of machine learning even for breaking crypto algorithms. So what has happened in the meantime? In 2016, there is a paper that shows that you can use deep learning to extract cryptographic keys from a cipher. And 2017, the certification bodies for some of the industries mandate that now you have to use deep learning in your evaluations. And this is for two reasons. Research in this area is very active for two reasons. On the first reason is that the knowledge to evaluate crypto algorithms so someone like Jane doing this activity would be very expensive. She would typically need to have a PhD in cryptography or an area of mathematics. Then she would need to have knowledge of statistics, and she would need to have also experience with real life targets, so work in the industry for a couple of years. So this kind of knowledge is very expensive. And on the other side, we know that in other areas of research, machine learning has brought on very impressive results. We have seen that machines have superhuman capabilities when we are classifying images, for example. So the question is then, can these machines do something similar for analyzing ciphers? So we definitely want to keep an eye on that. So how are we using machines in this case, so for side channel analysis? Well, basically, we are in a profile scenario in which means that we have a chip which is open, where we can set the keys, we can feed messages, we collect traces, and we are giving these traces to a machine. These are labeled traces. And machine constructs a model of what the leakage would be, and then it's using this model in the attack phase to classify targets. Now, in practice, the workflow looks a little bit like this. So we do acquisition, we collect traces, then we need to build a machine, and we use the machine for attack purpose. For building the machine, we actually have two stages. If any of you have built an AI machine, which I think is pretty common right now, you first need to construct, which means that you have to set the architecture, you need to set the hyperparameters for the machine, and then comes the phase of the training, in which you basically feed in data that you collected during the acquisition, and the machine basically updates itself, it updates its weight. But, and here is where the Jane has a problem. And the problem is that there is a big difference between how the side channel analysis community, how it's called, the community of doing analyzing ciphers by collecting power traces, and the deep learning community has. And the difference is that in the deep learning community, basically we are using things like loss and accuracy to train machines. And we know that our machine is doing well when these loss and accuracy functions are converging to values that are low or high respectively. But in side channel analysis, we are using different metrics. We are using something that is called key ranking and guessing entropy. And to this date, we do not have a direct relationship within these values. So then what Jane is facing at this point in time is basically she's training the machine using some metrics, but when using the machine, she's using different metrics. And therefore, we know that it is very hard to find what are the right parameters for a machine, or to train a machine in the right way for the right target. Also, for side channel analysis, and this is something that I forgot to say, for every target that you're evaluating, you basically need to collect new traces. You have to adapt your leakage model. So there is not, we cannot have one machine or one set of traces that you can apply to all evaluations. You have to do it for every board that you're evaluating. And as I said, this is a hard problem. We still don't know for the community how do we connect these 2 points. So now, and this is where the shameless plug of our work comes in, what we have done with our colleagues is we said, okay, if we don't know how to link these parameters, then why not try to see how the information in the machine is flowing? So that means that if we follow how the information about the data goes through the machine, we can decide if the machine is doing the right thing or not doing the right thing. It's the beginning. That's why here Jane is at the beginning of a big road. But it's a start that would help us, that can help us have more insight into how to solve this problem. And now, for the most technical part of my talk, I will briefly show you what this means. So, what we have here is basically a deep network. The gray layers are the network and the network layers, the hidden layers, and then the orange one is basically the hidden layer. And we are feeding the network with input data that is labeled, right? So in this case, we have power traces, and the labels are basically the target intermediate. And in order to see what is happening in the network, what we are doing is, we are also labeling the layers in the network. We are basically plotting what is called the mutual information between what the layer learns about the input. So the first term is the information that the layer has about the data, and on the other axis we have the information that the layer has about the labels. So we do this for every layer in the network, and then we observe what is happening. So how does this look like in real life, on a real cases? And here is, one back. So here is what the network does and what the network looks like in throughout the training epochs. So we see that in the first 4 layers, it knows a lot about both the data and the labels. However, the last layer, which are responsible with classification, in the beginning they know very little about both the data and the network. But as the training progresses, we can see that the information about both the data and the layer is progressing. And at the end of 200 epochs, we see that this information has reached almost its maximum capability. This is on training data. And without going into too much details, we discovered that the validation set, which is the set that you use to control what your training is doing, behaves slightly differently. So for the validation set, we discovered that the information about the data and the labels were not going up after all the layers, but there was an epoch after which the information about both the data and the labels started to decrease. And what we have done, we have taken snapshots of how the network looks like at the different epochs, and we performed experiments on how the machine is doing. And we discovered that the best epoch was that one where the information the mutual information is at its peak, and all other areas of the network showed worse results. And typically, to show that this is correct, what we have in what we are doing is we come up with graphs to show on real data that this is really that our metrics is the best. So I have here graph number 1, which shows this, and I also have a graph number 2, which shows the same thing. But I will not go into the details of what these graphs are. If you're interested, please come and talk to me during the breaks, or read the paper, or come to us. So to conclude my talk, as I said, what I would do is give a message to a younger self, myself 15 years ago, standing now here. So what I would tell myself would be the following. Never stop being the best version of yourself. We can always learn more, do more, and I think it opens up just possibilities for us. And the other one is never stop believing in yourself. I remember that sometimes in my career I choose to not apply for some things because I thought that the other candidates were better than me. Don't do that. Always try, always believe that you can do everything. And last but not least, I think we can all help Jane with her security evaluations.
Thank you, Ileana. Questions from the audience?
Hey, first of all, thank you for your talk. My question is, which machine learning models did you use for this task?
Sorry?
which deep learning models did you use for this task?
You mean which kind of architecture?
Yeah.
I think it was an MLP and a CNN. We used both.
Okay, interesting. And do you know which one performed better?
I think for us, we were not interested in that much about the network performance itself, but we were interested in whether the metric that we came up actually gives us the best version of the architecture that we were after. Does that answer your question?
Yeah, thank you.
More questions? I have one question. So I was wondering, do you need to do the training phase again for every new device, every new algorithm? Or is there something that can be transferred or learned from?
At this point in time, in best practices, we basically we know that the network architecture that best performs for side channel analysis are the CNNs. And we also have a model of how the architecture starts from. But yes, basically we have to start the training phase from scratch. And the area in which we are searching for what is the best architecture, or automatically searching for the best architecture, is still open.
Okay. One more question.
Hey, so I have been working in the space of side channel analysis, and it's very interesting to see the power of the side channels on the software when it's running. You need a few traces and you get the key. But it's a completely different story when we work on FPGAs, and I'm curious to know if you are running these deep learning models and how, applications for side channel on the FPGA fabric as well, or your analysis is based on the software attacks?
Thank you for that's a great question. We did notice indeed that doing machine learning for side channel analysis on the hardware traces is much more difficult than on the software traces. In the set that we have, in the sets that we have used for experiments, there is one which is collected on hardware devices, and we have used also that one to show that, for example, this metric is working. So it is possible to perform deep learning, or to use deep learning for the purpose of side channel analysis for hardware implementation, but it is a much more difficult task. There is one, we can take it offline, yes. Thank you.
Okay, so thank you, Ileana. And that concludes this session.